Welcome everybody, my name is Ricardo Vinuesa, and today we're going to continue with our series on machine learning with a very exciting method, which is SINDy. SINDy is the sparse identification of nonlinear dynamics, developed at the University of Washington with Steve Branton and Nathan Kutz. And it's a very interesting method because it goes in the direction of discovering equations. So this goes away a little bit from the classical or more, let's say, extended ideas of the deep learning, which is essentially a black box, right? And there's a little bit of work to be able to get some explainability from that. What we're trying to talk about today is a method that is inherently interpretable because we want to find covariant equations representing the data. So this is something that complements very well the more deep learning based techniques, and it can really help us to not only model systems, but also to identify some of the underlying physics and dynamics. So if you come with me to the board, we're going to be looking at the sparse identification of nonlinear dynamics, which is SINDy. So let's consider a nonlinear system. Okay, so for a nonlinear dynamical system, for instance, let's say that this system is x dot, which is some function of x. If we only have data, now we're going to assume that even if the data is produced from a set of covariant equations, we're going to assume that we don't know those equations because we want to be able to discover the underlying physics. In most cases, we won't even know the equations. So this is like pandemic data, for instance, or observations from stars, and we want to really look at the dynamics. We may not be able to know the equations. And if we don't know the equations, then we want to discover them. So that's a bit the idea. Even if we know something about the equations, we're going to assume that we don't know anything. So for a nonlinear dynamical system of this form, if we only have data, so we basically only have the observations, we don't have access to the function f, that means that we may not know the form of f. We may not know the form of f. Okay. Many dynamical systems have dynamics f with only a few active terms. And this is something that we can actually exploit, right? Because that will allow us to create a dictionary of possible terms. And then we're going to select which ones are active to represent the dynamics of our system. So we're going to take advantage of the fact that in many systems, it's only a few of those terms, such that we can guide with some intuition the creation of this dictionary. So many dynamical systems have dynamics f with only a few active terms in the space of possible right-hand side functions. Okay. In the space of possible right-hand side functions. That means that we're going to consider the possible functions to create the dictionary. Okay, so we consider possible forms for F, and let the data tell us which of these terms are actually active, right? Which of these terms are actually modeling the phenomenon that we have at hand, right? Given by the data. So, and let the data tell us which one is correct. Okay, so for example, one possibility could be the following system. X dot will be some coefficient A times X plus another coefficient B times X squared plus another coefficient C times X cubed plus a final coefficient D times X to the fourth power. So this is one possibility where our possible terms are actually polynomial functions, and our algorithm is going to select which terms from this polynomial distribution are actually representative of the data that we have in our system. So we're going to select the fewest number of non-zero terms. That's the idea. We want to have a parsimonious system. So we want to have as few terms as possible. So we want a model that is as simple as possible while still representing the physics of our system. If we add unnecessary terms, that's going to lead to overfitting, right? So that has problems with generalization, plus unnecessary complication of the interpretability and implementation of the model. So we want a simple model, but nothing simpler than that, right? We don't want to oversimplify because then our solution will not be correct. So we select the fewest, non-zero terms possible. Again, this is to keep it as simple as possible, but not simpler, right? That's kind of like the main thing. As simple as possible. Has to do also with Occam's razor, right? Of having the simplest explanation typically being the more correct one, but no simpler than that. So let's start by collecting time series of the data. Okay, this is always or typically the first step. If we don't know the equations or we assume that we don't know the equations, then we have data, and the data is going to be used to produce the model. So first we collect time series of the data. We collect time series of the data. And we're going to represent this with this X capital, which is basically the first snapshot, X at T1. This is now X at T2, and so on until X at T Madrid, okay? So these are the snapshots. We also want to collect time series of the time derivative, right? So we have all these snapshots at different instances in time. Now we want to calculate the time derivative. So also the time derivative. It's going to be important. So what I'm having here is X dot, which would be basically the X dot at T1, X dot at T2, all the way until X dot at T Madrid. Okay, so this is another snapshot over here. Now the next step, now we have the data, right? And remember our system looks like this if we go up, right? So our system is going to be X dot, which is some unknown function of X of the state of the system. Now we need to find, well, what happens with F. So we're going to build a library of candidate terms to basically form the functional distribution of this F over here. So we're going to build a dictionary, a possible library of terms, which we're going to distribute it as follows. We build a library. So then we build a library of nonlinear functions theta, nonlinear functions theta, theta of x, because this is, of course, going to depend on the data. Okay. So let's imagine that for this theta, we're going to have several possible terms. So theta of x will look like this, as follows. We're going to have some constant terms, some linear terms, some quadratic terms, okay, and so on until polynomials of degree d, so x to the d. But then we're going to have many more possible terms, including trigonometric functions. So this is the sine of x, for instance, and many more. Okay? What I want to illustrate with this, if we kind of go over here, is that this is an array of possibilities which involves constant terms. This would be the linear terms. Okay, this over here would be the quadratic terms. And of course, for the quadratic terms, we have many possibilities, right? Because then we can start, depending on how big is this x, right? And how many variables we have in our state. Let's imagine that our state is given by variable x1 and variable x2. Well, then the linear terms are going to be x1 and x2. But of course, the quadratic terms, this one over here, well, we can start to have x1 squared, x2 squared, and x1 times x2. So, of course, the number of possibilities increases as the size of the state increases and also as the polynomial order also rises. And that, of course, gives me many possibilities for possible terms. Now, people always ask me, so how are you choosing these terms, right? Where do you put a sign, or why don't you put an exponential or a logarithm? I mean, this, of course, the more terms you put in your dictionary, the more chances of discovering terms that will represent your data, but also you're complicating the procedure to select the right ones because you have many options, right? So typically it's a good idea to choose terms based on the underlying physics of the system that you're trying to model. So if your system is inherently periodic, then having trigonometric functions is going to be a good idea. If your system has some polynomial behavior, or if you know your system has some exponential growth, perhaps damped by some nonlinear damping while having exponential functions, and then combined with some other polynomial terms might be a good idea anyway. So try to get ideas and inspiration from the underlying physics of your system in order to properly choose the dictionary. Okay, that's another important point. So if we do that, if we express our dictionary theta like this, then we can express our system in matrix form as follows. Okay, so now we can write the dynamical system. So we can express the dynamical system as dynamical system as, and then what we have is the time derivative x dot is going to be equal to the unknown terms. So this would be basically the library of possible terms, the dictionary, theta of x, multiplied by a set of coefficients, right? Remember, if we go back to the example above, right, in here, the dictionary of terms would be the linear one, and then the quadratic, the cubic, and the fourth power. And then the unknown coefficients would be A, B, C, and D. So if we write that in matrix form, x squared, x cubed, and x fourth will be the theta of x. And then I'm going to encapsulate all the unknown coefficients in another matrix called xi. Okay, so A, B, C, and D would be making up this matrix xi, which contains those coefficients. So this will be basically something like this. Okay, and this is also a matrix over here. Okay, so this contains the unknown coefficients. This means that, of course, we have the data, right? This we know. We have created and chosen ourselves a dictionary, so we know that too. What we don't know are the coefficients. So what we should do now is solve for Xi. So we can solve, let's do it like this. We can solve for, and then the only thing we do is that we can basically isolate this Xi here. So we need to write it as follows. Like, so Xi would be equal if we pre-multiply on both sides by the pseudo inverse of theta, so basically theta plus. On the right-hand side, we're going to cancel and get the identity. On the left-hand side, what we will have is theta, which is a function of x. And this is now a plus, which means that we have the pseudo inverse multiplied by x dot over here. Okay. Now, a very important idea that we're going to explore a little bit in this video, and we will dive deeper into it in the next video, is the regularization. So if we want sparsity, and remember, we want sparsity because we want a model that is as simple as possible. So if in some of these, if some of the entries in theta, we have a fourth order polynomial, a 10th order polynomial, perhaps those would marginally improve the prediction of our data, but in a way that we are basically overfitting, because if we see new data, then the performance would not be so good. It's kind of like a spurious contribution to the performance. So a way to avoid that is to do regularization. And with regularization, we're making sure that essentially we only keep the most significant contributions to the performance of our model. Okay, so for sparsity, and sparsity means that many of these entries of Xi will be zero, so it will be a sparse vector, meaning that we have very few terms in our model. For sparsity, a good idea is regularization. Okay, we're going to get to that in just a second. Now, the columns of Xi, the columns of Xi, which are basically the Xi is the capital letter, the lowercase looks like this. So this would be the columns, right? The entries of this Xi matrix are going to be these columns, these vectors. These are vectors of coefficients. Vectors of coefficients determining the active terms. The active terms. So let's consider a convex L1 regularized regression. Okay, so considering this not only makes the optimization easier because we have fewer coefficients to optimize, but also makes the whole process easier from a computational point of view. So considering a convex L1 regularized sparse regression, what do we get? Well, psi k would be the argument of the minimum in psi k, so basically of all the possible entries of that column of this norm, which would be now x dot k. This is the kth column of x dot. So x k dot minus theta of x, like this, multiplied by psi k, and this is an L2 norm. Okay, so this is basically this. What this is telling me, just to kind of put things in perspective, is that I am basically solving this problem, right? I'm basically solving, let's make it a bit bigger, basically solving this problem, right? So I have, which we can solve like this. or like this with regularization. So I'm just minimizing the L2 norm of this guy, right? So it's x dot minus theta times psi, okay? This problem over here can be solved through inversion, right, with a pseudo inverse, or we can also regularize, as we're going to do in just a second. So the L2 norm is basically the solution of this problem. The only thing we are doing is take these two and move them to the left-hand side. Okay, that's the only thing we're doing. That's exactly what you can see here. Okay, that's the L2 norm. And then we're going to add plus lambda, which is our hyperparameter to set how strong we want to have the regularization. And now we have the L1 norm of psi k. Okay, this is the L1 norm. This is very important. So now we have two different important things here. This would be the kth column of x dot, okay? And this lambda is the sparsity promoting parameter. Promoting parameter. Okay. So if you remember from the previous videos, what we are doing with this is regularize, meaning that we are promoting the sparsity. So not only, so we want solutions of this psi, which minimize the L2 norm of this difference. So we want essentially a product of coefficients times the dictionary, right? That's the model that we want to have, which represent pretty well the data. That's what we want. But at the same time, we also want to keep the norm of those coefficients pretty low, right? So that means that we want to make sure that we are retaining only the coefficients which are significant. And so if we have coefficients of 10 to the minus 5, well, probably those ones will not really be having a significant contribution. They're just going to be overfitting. So we want to promote that sparsity in such a way that I can make zero all those small coefficients, right? So I can have a meaningful model. How is this lambda determined? It's a good question, and it depends a little bit on the type of data and the scale of the data, and also on how much you want to impose the regularization. There is a trade-off here, right? Because we are optimizing, meaning that the more I focus on keeping this sparsity, right, the worse the reconstruction. If I make many coefficients zero, in the extreme case, I will only have one coefficient or zero coefficients. So obviously I won't be able to have enough freedom to represent this data. On the other hand, if I make lambda zero, then I will not have any regularization, which means that I will have overfitting. I will have spurious coefficients contributing to my model. So there is a bit of a balance here, depending on the scale of the data, depending on the type of data, and also our experience and knowledge on the type of physics that we want to model. Okay. Now, how does one do this and this regularization? Well, this is one process, right? The L1 regularization. Next week, in the next video, we're going to look at another method, which is the STLS algorithm. This is a very, let's say, efficient and fine-tuned algorithm for this type of problems, which is going to really help us to do this in a bit of a more automatic way. Okay, so that's all we have for today. Feel free to reach out and ask questions if you have questions. Other than that, I'll see you next week with an implementation of the SINDy algorithm for practical problems. Thanks for watching and see you next time. Bye.